You are sitting where you always sit. Your body has weight. The room has edges. The air feels still. Nothing about this moment seems ambiguous. Your memories line up in a clean sequence. Yesterday led to today. Thought follows thought. Cause precedes effect. The world appears to be doing what it has always done, existing continuously, without interruption. That assumption feels so natural that you never question it. You assume that the universe prefers order over chaos. You assume that observers like you are rare, the result of long histories, stable laws, and improbable but meaningful chains of events. But physics does not share that preference. In the deepest layers of modern cosmology, there is a contradiction hiding in plain sight, a consequence of otherwise respectable equations, a result that emerges not from imagination, but from thermodynamics, probability theory, and the mathematics of infinite time. According to those models, the most likely explanation for your current experience may not be a long-lived universe that gradually produced you. It may be a single temporary fluctuation, a mind that assembled itself by accident, complete with memories it never lived. This is not a thought experiment. It is not philosophy dressed as science. It is a problem serious enough that physicists have spent decades trying to eliminate it from their own theories. It is called the Boltzmann Brain paradox. And if the universe we believe in is correct, then the paradox does not ask whether such minds can exist. It asks why you are not one of them. You trust continuity because it has never failed you. Your memories form a coherent story. A childhood, a past, a chain of experiences that feel anchored in something real. The universe appears to reward that trust. Stars persist. Atoms remain stable. Physical laws repeat themselves with mechanical consistency. But continuity is not a law of nature. It is an emergent pattern. Physics does not guarantee that moments must connect. It only describes how states evolve when they do. And once you remove the assumption that the universe must behave in ways that feel intuitive, the stability you rely on becomes a statistical preference, not a certainty. From your perspective, continuity feels fundamental. One moment flows into the next without interruption. Consciousness feels like a thread, not a sequence of disconnected frames. You wake up expecting the same world you fell asleep in, and so far, that expectation has been justified. But physics does not recognize expectations. It recognizes configurations of matter and the rules governing their transitions. At the most basic level, the universe is not built from stories or sequences. It is built from states. At one instant, particles occupy certain positions, carry certain energies, and interact in certain ways. At the next instant, those values change according to physical laws. The laws do not insist that those instants must feel connected to an observer inside them. They only describe what happens if a transition occurs. Continuity, then, is something you infer after the fact. You look at a series of closely related states and interpret them as a single unfolding process. Memory stitches those states together. Identity smooths over the gaps, meaning fills in what physics leaves unspecified. None of this is required by the equations themselves. In everyday conditions, this distinction does not matter. The universe around you is stable enough that continuity is overwhelmingly likely. Large structures persist. Brains do not randomly disassemble. Your environment remains close to the same configuration from one moment to the next. Under those conditions, assuming continuity is not just reasonable, it is unavoidable. But this reliability is contingent, not guaranteed. Thermodynamics tells you that order persists only when it is supported. Systems naturally drift toward equilibrium, toward states that can be realized in more ways. Continuity survives because the universe, at your scale and at this time, happens to support it. Not because it must, but because it usually does. The danger appears when you extrapolate that local reliability into a global principle. When you assume that because continuity holds here and now, it must hold everywhere and always. Physics does not make that promise. In fact, under many cosmological models, it explicitly refuses to. Once time stretches long enough, once space grows large enough, rare events stop being negligible. The assumption that the universe must move smoothly from past to future becomes a convenience, not a rule. A pattern that holds because the conditions are favorable, not because reality demands it. Your sense of self depends entirely on that pattern. Identity requires persistence. Experience requires sequence. Memory requires causation. Remove continuity, and the idea of a self dissolves into a set of isolated configurations with no necessary relationship to one another. Yet physics allows such configurations. It allows isolated states that look exactly like you at this moment, complete with memories of a past that did not occur, and expectations of a future that will never arrive. Nothing in the laws forbids a moment from existing alone. You rarely consider this possibility because your experience does not encourage it. Everything you have ever observed supports the illusion that moments must belong to a chain. That illusion is strong enough to feel like a necessity, but it is learned, not enforced. Continuity survives because the universe has not yet challenged it at scales you can feel. But when physics examines reality without reference to comfort or intuition, continuity loses its privileged status. It becomes one outcome among many, favored by certain conditions and abandoned by others. The unsettling implication is not that continuity will suddenly fail. It is that it never had to succeed in the first place. At the foundation of this problem is entropy, not disorder, but probability. Entropy measures how many ways a system can exist while appearing the same. A tidy room has very few such arrangements. A messy one has countless possibilities. Left alone, systems drift toward states that can be realized in more ways, not states that feel purposeful. The unsettling implication is simple. Given enough time, improbable arrangements do not just become possible. They become inevitable. Not because the universe wants them, but because it tries everything. You tend to think of entropy as decay, as things breaking down, wearing out, falling apart. That intuition is not wrong, but it is incomplete. Entropy does not care whether a state is useful, beautiful, or meaningful. It only cares about how many versions of that state exist. Probability, not purpose, drives the direction of time. When a system changes, it does not move toward what feels likely to you. It moves toward what is statistically dominant. A low entropy configuration, like a functioning machine or a living organism, occupies a narrow region of possibility space. There are relatively few ways for it to exist while remaining intact. A high entropy configuration occupies a vast region. There are countless ways for it to be broken, scattered, or unstructured. This asymmetry explains why order is fragile and chaos is persistent. But it also explains something more disturbing. If a configuration is allowed by the laws of physics, then it exists somewhere in the space of possibilities. And if time is long enough, the system will eventually wander into it, no matter how implausible it seems. You rely on the improbability of certain events as if improbability were a barrier. You assume that because something is unlikely, it can be ignored. That assumption holds only when time is limited. Entropy does not protect you from rare outcomes. It guarantees them, given sufficient opportunity. Consider a gas in a sealed box. Almost all of its possible states involve the molecules being spread evenly. That is why the gas stays diffuse. But nothing in physics forbids all the molecules from clustering spontaneously into one corner. That configuration is astronomically unlikely, but not impossible. Given enough time, it must occur, not once, but endlessly. The same logic applies to every physical system, including systems complex enough to think. Entropy does not distinguish between trivial fluctuations and extraordinary ones. It treats them all as points in probability space. A slight rearrangement of particles is more likely than a dramatic one, but both are permitted. The difference is not categorical. It is numerical. This is where meaning quietly collapses. Meaning depends on context, history, and function. Entropy recognizes none of these. A configuration that looks like a working brain and a configuration that looks like scattered matter are judged solely by how many ways they can be realized. If a functioning brain occupies a tiny region of possibility space, that does not disqualify it. It only makes it rare. Rarity does not imply irrelevance in an infinite universe. It implies eventual repetition. You might assume that complexity protects you, that the more elaborate a structure is, the safer it is from random emergence. Entropy offers no such reassurance. Complexity is simply another pattern. If the pattern is physically allowed, it belongs to the set of possible states. Time does not forget what is possible. This is why entropy is dangerous when combined with infinity. Over short durations, entropy produces decay. Over long durations, it produces everything. The universe does not need to aim for a result. It does not need a mechanism that assembles meaning piece by piece. It only needs time and permission. Given those, even the most structured, specific, and fragile configurations will appear. And when they do, entropy does not ask whether they make sense. It does not check whether they belong in a story. It does not care whether they have a past or a future. It only registers that, for a moment, this arrangement exists. That indifference is the foundation of the Boltzmann Brain paradox. In the 19th century, Ludwig Boltzmann proposed something radical. If the universe tends toward disorder, then any appearance of order must be temporary, a fluctuation away from equilibrium. In his view, the orderly universe you observe might not be the default state at all. It could be a rare deviation, a brief statistical accident in an otherwise featureless cosmos. At the time, this idea was meant to explain why the universe appears structured at all. Boltzmann did not realize that the same logic would later undermine the observer making the observation. You have to place yourself in Boltzmann's position to understand the weight of the idea. Physics was struggling with a contradiction. The laws governing microscopic particles were time-symmetric. They worked the same whether time moved forward or backward, and yet the macroscopic world clearly was not. Ice melts, smoke disperses, order fades. Boltzmann's statistical interpretation of entropy offered a solution. Time does not have a preferred direction because the laws demand it, but because probability does. From this perspective, the universe does not move toward disorder because it must. It moves that way because disordered states are overwhelmingly more numerous. Order survives only as long as a system happens to occupy a rare, constrained configuration. Eventually, probability wins. Boltzmann took this logic seriously, perhaps too seriously. If entropy increases with time, and if the universe has existed long enough, then equilibrium should already have been reached. A uniform, featureless state with no structure, no stars, no planets, no observers. But you are here. The universe is structured. Something does not add up. Boltzmann's answer was not that the laws were wrong, but that the situation you observe is atypical. You are not living in the standard state of the universe. You are living in a fluctuation, a temporary pocket where entropy has dipped low enough for complexity to exist. Outside that pocket, equilibrium reigns. In this picture, the universe at large is mostly empty, uniform, and inert. What you call reality is a statistical anomaly. A deviation so rare that it appears special only because you happen to be inside it. At the time, this was an elegant move. It preserved the second law of thermodynamics while explaining why you see structure instead of heat death. It did not require new forces or hidden mechanisms. It relied entirely on probability and time. What Boltzmann did not fully confront was the scale of the explanation. If you allow fluctuations, you must allow all of them, small ones, large ones, and everything in between. A fluctuation large enough to produce a universe like the one you observe is extraordinarily rare. It requires an immense, coordinated departure from equilibrium. Entire galaxies, cosmic microwave background patterns, consistent physical laws across vast distances. The probability is not just small, it is vanishing. But the probability of a much smaller fluctuation is far higher. A fluctuation that produces a single localized structure, a planet-sized region, a laboratory, a brain. Boltzmann did not frame his idea in terms of observers. He framed it in terms of macroscopic order. But the logic does not stop there. If the universe can fluctuate into an ordered state, it can fluctuate into any ordered state, including one that contains an observer with memories. From the inside, that observer would see exactly what you see now, a world that appears stable, a past that seems coherent, laws that feel consistent. Nothing in the experience would reveal its true origin. Boltzmann's insight solved one problem and planted another. It explained why order exists at all, but it also made order arbitrary, not the result of history, but of chance. Not a foundation, but a coincidence. Once that shift occurs, the role of the observer changes. You are no longer guaranteed to be a product of a long, continuous process. You are merely a configuration that happens to exist. And if that configuration can arise briefly, then the universe does not need to build you slowly. It only needs to stumble into you. That possibility remained dormant for decades. But when cosmology expanded Boltzmann's idea to infinite time and space, the implication could no longer be ignored. Modern cosmology introduces a dangerous ingredient: infinity. Many leading models allow the universe to exist for an arbitrarily long time, not just billions of years, but forever. And in an infinite timeline, probability behaves differently. Even the rarest events occur endlessly, not once, not occasionally, but infinitely many times. That includes events so unlikely that they should never matter. And once you accept that, you are forced to confront a disturbing hierarchy of observers. You are accustomed to treating probability as a filter. Improbable events fade into irrelevance. They are dismissed not because they are impossible, but because there is not enough time for them to occur. Infinity removes that protection. In a finite universe, probability has weight. A 1 in a trillion event can be ignored if the system does not have enough opportunities to realize it. In an infinite universe, opportunity never runs out. Probability stops acting like a gatekeeper and becomes a guarantee. This is not a philosophical trick. It is a mathematical consequence. If an event has any non-zero probability, no matter how small, then given infinite trials, it must occur, not just once, but without limit. The universe does not choose which outcomes feel reasonable. It exhausts the entire space of allowed possibilities. This changes the meaning of rarity. Rare no longer means negligible. It means delayed. Given infinite time, every allowed configuration becomes common in the sense that it occurs endlessly. You might try to avoid this by arguing that the universe does not repeat itself, that conditions change, that states drift. But infinity is indifferent to drift. If the laws of physics remain stable, then the set of allowed configurations remain stable. Time simply ensures that all of them are eventually visited. This is where intuition fails. You are trained by experience to think in terms of typical situations. Infinite time destroys the concept of typicality unless it is carefully defined. What does it mean to be typical in a universe where every outcome occurs infinitely many times? Cosmology is forced to answer this question because observers are not interchangeable. They differ in complexity, duration, and reliability. Some persist for billions of years. Others exist for fractions of a second. Some arise through long causal histories. Others appear fully formed. Infinity does not prefer the meaningful over the meaningless. It does not reward stability. It only counts occurrences. Once you accept infinite time, you must rank observers not by their depth, but by how frequently they occur. This creates a hierarchy that feels backward. Simple observers dominate because they require fewer constraints. Short-lived observers dominate because they are easier to produce. Accidental observers dominate because they do not require a universe to support them. In this hierarchy, a single isolated brain formed by chance is vastly more probable than an entire civilization evolving over billions of years. The universe does not need to assemble stars, planets, chemistry, and biology. It only needs to briefly align particles into a functional pattern. From a probabilistic standpoint, this is efficient. From a human standpoint, it is catastrophic. You are forced to ask where you belong in this hierarchy. If you assume you are a random observer drawn from all observers that ever exist, then infinite time heavily biases the selection toward the simplest possibilities, toward observers with no genuine past and no enduring future. This is not an abstract concern. Scientific reasoning relies on the assumption that you are not an extreme statistical anomaly, that your experiences are representative enough to trust. Infinite time threatens that assumption by flooding the universe with observers whose experiences are fundamentally misleading. Once this flood exists, being a long-lived observer with a coherent history becomes the exception, not the rule. And exceptions cannot ground reliable knowledge. Infinity does not just expand the universe. It destabilizes explanation. It turns probability against meaning and abundance against truth. This is why infinite time is not a neutral assumption. It quietly rewrites what it means to exist, to observe, and to know. And once it is introduced, there is no simple way to contain its consequences. You assume that minds require histories. Brains need evolution. Neurons need development. Memories need causes. But physics only requires arrangement, not origin. If a configuration of particles matches the physical structure of a functioning brain, then according to the laws of physics, that brain exists, even if it formed spontaneously, even if it lasts only a fraction of a second. That fleeting configuration would still have thoughts, still have perceptions, still believe it remembers a past. This is where intuition resists most strongly. You have never encountered a mind without a story behind it. Every person you know grew from a body that developed gradually. Every thought you have seems tied to earlier experiences. Cause and effect feel inseparable from consciousness itself. But physics does not encode that relationship. It does not contain a rule stating that a brain must be built slowly or that memories must correspond to real events. It only specifies which arrangements of matter produce which behaviors. If the arrangement is present, the behavior follows, regardless of how that arrangement came to be. A memory, at the physical level, is not a record of the past. It is a present configuration of neural states. Electrical potentials, synaptic weights, molecular patterns. Physics does not tag these states with their origins. A memory formed through years of experience and a memory formed through random assembly are identical if the configuration is the same. From the inside, there is no difference. You might think that time is required for thought, that consciousness needs duration to arise. But thought is not a process that waits for validation. It is a physical event unfolding moment by moment. If the brain exists for even an instant in a functioning state, that instant contains experience. This is uncomfortable because it strips consciousness of its narrative privilege. The mind does not inherently know whether it has earned its memories. It simply finds them already there. A sense of personal history is not evidence of an actual history. It is a byproduct of how brains encode information. In everyday life, this distinction never matters. Brains do not assemble spontaneously around you. They are products of biology, sheltered by stable environments. But when cosmology expands the scale of what is allowed, biology stops being the only path to cognition. A mind does not require a childhood. It does not require learning. It does not require survival. It requires only the right physical pattern, sustained long enough for awareness to occur. You might object that such a mind would immediately fall apart, that it would be unstable, incoherent, unable to function. That may be true in most cases, but stability is not required for belief. Coherence is not required for experience. Even a brief, fragile mind can contain a complete subjective world. In fact, instability can be hidden. The mind could believe it is stable, even as it dissolves. It could believe it is embedded in a larger universe, even if that universe does not exist beyond its immediate perception. Nothing in its experience would contradict that belief, because there would be no time for contradiction to arise. This reveals a quiet asymmetry. To be a real observer, you do not need a real past. But to know you have a real past, you would need more than experience can provide. Experience only ever accesses the present. Physics allows configurations that imitate everything you associate with identity: personality, memory, expectation, selfhood. None of these require continuity. They only require structure. Once you accept this, the idea of a mind appearing without a past stops being mysterious. It becomes a simple consequence of treating consciousness as a physical phenomenon, rather than a privileged one. The unsettling part is not that such minds are possible. It is that from the inside, they are indistinguishable from you. And in a universe where time and opportunity are unbounded, possibility quietly turns into abundance. A Boltzmann brain is not a metaphor. It is a literal object, a self-aware mind that forms due to random thermal fluctuations. It does not evolve. It does not learn. It does not survive. It simply appears, fully formed, complete with a false internal narrative, and then dissolves back into chaos. From the inside, however, it feels no different from you. To understand why this idea is taken seriously, you have to strip away any remaining intuition about what the universe is allowed to do. Thermal fluctuations are not rare curiosities. They are built into the fabric of physical law. Particles constantly exchange energy. Fields fluctuate. Even in regions that appear empty and cold, microscopic deviations never stop occurring. Most of these fluctuations are small. A particle momentarily appears. A bit of energy briefly concentrates before dispersing. These events are usually insignificant and unobservable, but the laws governing them do not impose a maximum scale. They impose only a probability. If the universe exists long enough in a state that allows fluctuations, then configurations of any complexity are permitted. Not likely, not common, but allowed. And allowed is enough. A Boltzmann brain is simply the name given to one such configuration. A particular arrangement of matter and energy that, for an instant, realizes the physical structure of a functioning brain. Neurons are in place. Signals propagate. Memories are encoded. Consciousness ignites. There is no womb, no development, no environment that nurtured it. The brain does not need to be attached to a body. It does not need sensory organs connected to a real world. The internal processes alone are sufficient to generate experience. Perception does not require accuracy. It requires activity. For the brief moment it exists, the Boltzmann brain thinks. It registers sensations. It reflects. It believes. The belief may include a detailed history, a life story, a sense of being embedded in a vast, stable universe governed by consistent laws. That belief is not a mistake from the brain's perspective. It is the only information available. The brain has no access to the external conditions that produced it. It cannot compare its memories to reality. It can only trust the structures that constitute its mind. You might assume that such a brain would be immediately aware of its instability, but awareness does not include diagnostics. A mind does not automatically know whether it will persist. It assumes continuity because continuity has been encoded as an expectation. That expectation can exist even if it will never be fulfilled. From the outside, the Boltzmann brain is a transient fluctuation. From the inside, it is a complete world. Duration does not scale with significance. A moment of consciousness is still consciousness. This is what makes the concept so difficult to dismiss. There is no contradiction in the physics. There is no violation of known laws. The discomfort arises entirely from the implications, not from the mechanism. Once you accept that such brains are physically possible, the next question is unavoidable. How many of them are there? In a universe with finite time and volume, the answer could be zero, or close enough to zero that the concept remains theoretical. But in a universe with infinite time, even the rarest fluctuations repeat endlessly. And among all possible observers, Boltzmann brains are among the simplest to produce. They do not require stars. They do not require chemistry. They do not require planets or ecosystems. They require only a brief, localized alignment of particles. Compared to the astronomical cost of evolving intelligent life through billions of years of cosmic history, a Boltzmann brain is cheap. Probability favors the cheap over the elaborate. This leads to a quiet inversion. The observers you assume are typical may be extraordinarily rare. The observers you never encounter may dominate existence. The first Boltzmann brain is not important because it exists. It is important because, once allowed, It threatens to redefine what it means to be an observer at all. And that threat does not stay theoretical for long. Here is where probability becomes unforgiving. Creating an entire universe like the one you believe you inhabit requires an immense deviation from equilibrium. Galaxies, stars, planets, chemistry, biology, and history all need to align. Creating a single brain requires far less structure, fewer particles, less coordination. In an infinite universe, the easier outcome dominates. That means isolated minds vastly outnumber evolved civilizations. You are used to thinking of complexity as impressive. Difficult things feel special because they require effort, time, and precision. A civilization seems more significant than a momentary thought. A universe seems more meaningful than a single mind. But probability does not rank outcomes by significance. It ranks them by cost. Cost, in this context, means constraint. How many conditions must be satisfied at once for something to exist? The more conditions required, the smaller the region of possibility space that outcome occupies. The universe does not favor outcomes that feel rich. It favors outcomes that are easy to assemble. An entire cosmological history is extraordinarily expensive. It demands a low-entropy initial state. It demands stable physical laws over billions of years. It demands stars that burn long enough, planets that remain intact, chemistry that allows complexity, and evolutionary pathways that do not collapse before intelligence emerges. Each layer narrows the set of allowed states. A single functioning brain requires far less. It does not need a stable star. It does not need an ecosystem. It does not need a planet that survives geological timescales. It does not need to reproduce or persist. It needs only to exist briefly in the right configuration. From a probabilistic perspective, this difference is decisive. In an infinite universe, outcomes are not weighted by depth or richness. They are weighted by how often they occur. If one type of observer requires vastly fewer constraints than another, then it will appear vastly more frequently, even if each appearance is fleeting. This creates a hierarchy that feels inverted. Long-lived observers embedded in coherent worlds feel fundamental to you because you are one of them. But probability does not care about perspective. It counts instances, not narratives. Imagine cataloging every observer that ever exists across infinite time. Each evolved civilization contributes a limited number of observers over its lifespan. Each Boltzmann brain contributes exactly one. But Boltzmann brains can appear anywhere, anytime, without preparation. Their production is not bottlenecked by cosmic history. As time stretches toward infinity, the count diverges. The number of evolved observers remains finite or grows slowly. The number of simple observers grows without bound. This is not because the universe prefers deception. It is because the universe prefers efficiency. You might assume that complexity should win because it builds on itself, that civilizations can generate many minds once established. But even that advantage is dwarfed by the sheer availability of opportunities for simple fluctuations. A civilization must survive to create observers. A fluctuation does not. The paradox sharpens when you consider typicality. If you are randomly selected from the set of all observers that ever exist, probability says you should expect to be among the most common type, not the most elaborate, not the most meaningful, the most frequent. That expectation clashes violently with your experience. You perceive a vast, structured universe with consistent laws and deep history. You are not a disembodied thought blinking into existence. You are embedded in a world that appears stable and shared. Probability says that experience is rare. This does not mean it is impossible. It means it is atypical under certain assumptions. And science relies on the assumption that your observations are not wildly atypical. Without that assumption, inference collapses. The unforgiving part of probability is that it does not negotiate. If simpler observers outnumber complex ones by an infinite margin, then any theory predicting that outcome forces you into a corner. Either you accept that you are extraordinarily unrepresentative, or you reject the theory. This is why the Boltzmann Brain paradox is not about exotic minds. It is about numbers, about counting, about what dominates when limits are removed. The universe does not need to erase meaning to overwhelm it. It only needs to make meaning expensive. And in the presence of infinity, expensive outcomes quietly disappear into insignificance. You assume you are a typical observer. That assumption is built into almost all scientific reasoning. But if Boltzmann brains dominate, then a randomly selected observer is far more likely to be one of them than a being embedded in a coherent universe. This creates a contradiction. If your theory predicts that most observers are deluded, then it undermines the reliability of observation itself, including the observations that support the theory. You rarely notice this assumption because it is so deeply embedded in how you think. When you interpret data, you assume your measurements are not pathological. When you reason about the universe, you assume your perspective is not an extreme outlier. Science does not work without this quiet premise. Evidence only matters if the observer collecting it can be trusted to be representative. This idea is known as typicality. It is not a physical law. It is a methodological necessity. You assume that, given a correct theory, your observations should be reasonably likely under that theory. Not guaranteed, but not vanishingly rare. Boltzmann brains threaten this assumption at its core. If a cosmological model predicts that the vast majority of observers are momentary fluctuations with fabricated memories, then being a long-lived observer with a coherent past becomes an anomaly of staggering improbability. Under such a model, your experience is not just unlikely, it is statistically suspicious. This creates a self-referential problem. You are using your observations to justify a theory that claims your kind of observer is unreliable. The more successful the theory is at predicting Boltzmann brain dominance, the less reason you have to believe it. This is not a matter of comfort or intuition. It is a logical failure. Imagine a theory that predicts that almost all measuring devices malfunction randomly, occasionally producing correct readings by accident. Even if such a theory fits some data, you would have no reason to trust the data it fits. The act of confirmation would be meaningless. Boltzmann brain-dominated universes suffer from the same defect. If most observers are deluded, then observation itself becomes a poor guide to truth. Memory becomes suspect. Records become unreliable. Inference loses its footing. You might try to escape this by insisting that you are not randomly selected, that your position is special, that you are conditioned on being an observer with coherent experiences. But this move quietly reintroduces the assumption you were trying to justify. It selects the outcome that preserves meaning without explaining why that selection is valid. Typicality is not optional. Without it, probability statements collapse. Predictions lose relevance. Science becomes a catalog of possibilities with no way to privilege one over another. This is why physicists take the observer problem seriously. It is not about strange minds appearing in empty space. It is about whether the universe you describe allows you to know anything about it at all. A theory that predicts your experiences are overwhelmingly likely to be false is not merely unsettling. It is unusable. This forces a reckoning. Either the universe is structured in such a way that typical observers have reliable experiences, or the concept of empirical knowledge dissolves. There is no middle ground. Boltzmann brains expose a fault line between mathematical consistency and epistemic viability. A theory can be internally coherent and still destroy the conditions required for believing it. That is why this paradox cannot be dismissed as a curiosity. It attacks the foundation of scientific reasoning. It asks whether the universe you model is one in which modeling is possible. If the answer is no, then the model must be rejected, not because it is wrong in detail, but because it invalidates the act of knowing itself. And that realization leads to an uncomfortable conclusion. Reality is not judged solely by what it permits. It is judged by what it allows you to trust. Once that criterion is introduced, physics is no longer free to explore every mathematically allowed universe. Some possibilities are excluded not because they are impossible, but because they would leave you unable to know that anything is possible at all. That is the observer problem. And once you see it, you cannot look away. A theory that predicts mostly false observers cannot trust its own confirmation. If the majority of observers are momentary fluctuations with fabricated memories, then empirical evidence loses its authority. Measurements, experiments, and reasoning become statistically suspect. This is not just unsettling, it is logically corrosive. A scientific theory that destroys the credibility of observation cannot survive unchanged. Science depends on a fragile loop. You observe the world, infer laws, and then use those laws to predict further observations. The loop only works if observation itself is reliable, not infallible, but grounded. Once that grounding is removed, the loop collapses into self-reference. Boltzmann. Brain-dominated theories break this loop from the inside. If most observers arise through random fluctuations, then most experiences are not connected to a real external world in the way you assume. Their memories do not track history. Their perceptions do not reflect stable environments. Their conclusions are not constrained by continuity. They are statistical accidents that briefly resemble understanding. Under such conditions, evidence stops being evidence. A measurement does not indicate a law. A record does not indicate a past. A theory does not indicate truth. It only indicates that, by chance, a particular configuration of matter happened to contain that belief. You might think that this problem only affects hypothetical observers, not you. But the theory does not make that distinction. It treats all observers symmetrically. If false observers dominate, then the probability that you are one of the reliable exceptions becomes vanishingly small. That probability is not just low, it is incompatible with rational belief. Scientific reasoning assumes that you are not overwhelmingly likely to be mistaken about everything. That assumption is not proven by science. It is a prerequisite for science. Without it, no amount of data can justify confidence. This is why Boltzmann brain scenarios are considered pathological. They do not merely predict strange outcomes, they predict the erosion of epistemic trust. A universe where knowledge is statistically unlikely is a universe where knowledge cannot function. Imagine trying to validate a theory in such a universe. You collect data, you see patterns, but the theory itself tells you that such patterns are probably illusory, the result of chance alignments in unreliable minds. The more you rely on observation, the more the theory undercuts the legitimacy of that reliance. This is a form of self-undermining that science cannot tolerate. Importantly, this is not a philosophical complaint layered on top of physics. It arises directly from the probabilistic structure of the theory. If the predicted distribution of observers overwhelmingly favors unreliable ones, then reliability becomes an exception that requires explanation. Physics does not get to ignore that requirement. The problem is not that Boltzmann brains are strange. It is that they outnumber everything else. If they were rare, they would be curiosities, but when they dominate, they become the standard, and standards define what counts as evidence. At that point, confirmation loses meaning. A theory confirmed by observers it predicts should not exist, as reliable entities is not confirmed in any meaningful sense. It is a model that consumes its own justification. This is why physicists describe such theories as unacceptable, not incorrect, but incoherent in a deeper way. They fail not because they contradict data, but because they strip data of its authority. To preserve scientific reasoning, something has to give. Either the cosmological assumptions that lead to Boltzmann brain dominance must be revised, or the framework for interpreting probability and observation must be restructured. Most researchers choose the former. They treat self-undermining theories as signs that an assumption has gone too far. Infinite time, infinite space, unregulated measures. Somewhere, the model has crossed a boundary. This response is pragmatic, not emotional. Science does not reject these theories because they are disturbing. It rejects them because they are unusable. A theory must allow itself to be known. If it predicts that knowing is almost always an illusion, it disqualifies itself. That is the quiet line Boltzmann brain scenarios cross. They do not merely describe a strange universe. They describe a universe where description itself has no standing. And physics, if it is to remain physics, cannot accept that. Physicists did not ignore this problem. They recognized it as a fatal flaw. If a cosmological model predicts Boltzmann brain dominance, it is considered unacceptable, regardless of how elegant its equations appear, not because it feels disturbing, but because it collapses the foundation of scientific inference. This forced researchers to re-examine assumptions they had previously treated as harmless. For decades, cosmology had been guided by a simple ambition: describe the universe as it is, using mathematics that extends as far as possible without contradiction. Infinity was not feared. It was embraced. Eternal expansion, endless inflation, unbounded time horizons all seemed like natural extrapolations of successful theories. The Boltzmann brain paradox changed the tone of that confidence. It revealed that certain assumptions, while mathematically consistent, carried consequences that science could not live with. A model could be internally flawless and still be epistemically destructive. That realization marked a quiet crisis. Not a public one, but a conceptual one, discussed in papers and conferences with careful language and restrained urgency. The crisis was not about strange minds appearing in empty space. It was about what happens when explanation outpaces justification. When a theory explains everything, but in doing so, explains away the credibility of explanation itself. Cosmology had reached a point where it could no longer evaluate theories solely on their ability to match observations or unify equations. It had to ask a more uncomfortable question. Does this theory allow observers like you to exist as reliable witnesses? This was a new criterion, and it was not optional. If a model implied that the overwhelming majority of observers were unreliable, then the minority of reliable ones could not rationally claim to confirm the model. The confirmation would be statistically meaningless. The theory would be sawing off the branch it stood on. This forced a reversal of perspective. Instead of starting with equations and asking what kinds of observers they permit, physicists began asking what kinds of observers must be permitted for physics to function at all. Assumptions once considered neutral suddenly became suspect. Infinite time, infinite volume, certain measures used to count events across space-time. Each of these, when combined with otherwise reasonable physics, pushed the universe toward Boltzmann Brain dominance. The crisis was not that one model failed. It was that many promising models failed for the same reason. Eternal inflation, once celebrated for its explanatory power, became a source of unease. De Sitter space, a simple solution to Einstein's equations with a positive cosmological constant, appeared to harbor an unavoidable Boltzmann brain problem if it persisted indefinitely. Dark energy, a pillar of modern cosmology, now carried epistemic risks alongside its empirical success. None of this meant that the observations supporting these ideas were wrong. It meant that extrapolating them without constraint led to worlds where observation itself could not be trusted. This is a subtle failure mode. A theory does not contradict data. It contradicts the act of using data. In response, cosmologists did something unusual. They began rejecting theories not because they were disproven, but because they were too permissive, too generous with possibility, too willing to allow universes in which knowledge dissolves. This was not censorship. It was triage. Science requires a stable platform from which to reason. If a model erodes that platform, it must be modified or discarded, regardless of how compelling its mathematics may be. The Boltzmann Brain paradox forced cosmology to confront a limit, not a limit of computation or observation, but a limit of acceptable explanation. Beyond that limit, theories become indistinguishable from stories that explain everything and therefore explain nothing. The crisis did not end with a dramatic resolution. There was no single paper that closed the case. Instead, there was a gradual shift in standards, a recognition that some infinities are not merely difficult, but corrosive. Cosmology survived by becoming more cautious, by admitting that not every mathematically allowed universe is a universe science can inhabit, and in doing so, it quietly acknowledged something unsettling, that the universe physics describes must be constrained not only by what can exist, but by what can be known. That realization reshaped the field, and it left a lingering question that no equation alone could answer. Dark energy accelerates the expansion of the universe. Its presence changes everything. In many models, accelerated expansion creates vast cold regions approaching thermal equilibrium, perfect conditions for rare fluctuations over infinite time. Ironically, the same mechanism used to explain cosmic structure threatens to drown it in meaningless observers. You encounter dark energy as a measured fact before you encounter it as a problem. Galaxies are receding faster than they should. The expansion of space is not slowing down. It is speeding up. To account for this, cosmology introduces a pervasive component of reality that does not clump, does not dilute, and does not fade as the universe grows. Dark energy fills space evenly. As space expands, more of it appears. This has a subtle but profound consequence. As the universe accelerates, regions of space become increasingly isolated from one another. Matter thins out, stars burn out, galaxies slip beyond causal contact. What remains is an ever-expanding volume of near-empty space, cooling toward equilibrium. At first, This seems like the quiet ending of cosmic history, a slow fade into darkness. But from the perspective of statistical physics, this is not an ending at all. It is an environment. A universe dominated by dark energy asymptotically approaches a state similar to de Sitter space, a space-time with a horizon, a temperature, and persistent quantum fluctuations. It is not perfectly empty. It never settles completely. There is always a background hum of microscopic activity. Given enough time, that hum becomes dangerous. In these cold, dilute regions, entropy is already near its maximum. Large structures are gone. The universe has little left to do. And yet, because time stretches on without limit, the rare fluctuations permitted by physics have endless opportunities to occur. This is where dark energy intersects with the Boltzmann brain problem. Accelerated expansion creates enormous volumes of spacetime that remain stable for unimaginably long durations. These regions do not collapse. They do not recycle matter into new stars. They simply persist. And persistence is exactly what rare fluctuations require. A fluctuation that produces a star is unlikely. One that produces a galaxy is vastly less so. But a fluctuation that produces a localized, transient configuration, such as a brain-sized structure, is comparatively cheap. Dark energy does not create Boltzmann brains directly. It creates the conditions in which they dominate. By stretching the universe thin and allowing it to exist indefinitely in a near equilibrium state, dark energy provides an infinite stage on which probability can exhaust itself. This is the irony. Dark energy was introduced to explain why the universe looks the way it does at large scales. It helps account for the observed distribution of galaxies and the history of cosmic expansion. It fits the data. But when extrapolated into the far future, it predicts a universe where the meaningful structures it helped explain are statistically overwhelmed by meaningless ones. The problem is not dark energy itself. It is what happens when its effects are allowed to run forever without constraint. Eternal accelerated expansion turns the universe into a factory for minimal observers, minds without worlds, experiences without histories. You might think that the emptiness would suppress complexity, that as matter thins out, nothing interesting could happen. Entropy suggests the opposite. Once equilibrium is reached, the system explores all allowed microstates given enough time. Complexity does not vanish, it becomes accidental. In a dark, energy-dominated universe, stars and planets are rare and temporary, but thermal fluctuations never stop. And among all possible fluctuations, those that require the least deviation from equilibrium occur most often. That puts isolated observers at the top of the statistical hierarchy. This realization forced cosmologists to reconsider how seriously to take eternal acceleration. A universe that expands forever under dark energy may be mathematically consistent and empirically supported in the present, but it leads to an observer landscape that erases the significance of observation. The threat is not immediate. It unfolds over timescales so vast they resist comprehension. But infinity does not care about delay. If a process is allowed and time is unbounded, the outcome is unavoidable. Dark energy, once a solution to a mystery, becomes part of a deeper problem. It stabilizes space-time just enough to let probability run unchecked. It turns emptiness into opportunity. And in doing so, it quietly raises a question that cosmology cannot ignore: whether a universe that expands forever is a universe that can still mean anything at all. Quantum fields fluctuate even in empty space. This is not hypothetical. It is experimentally confirmed. Particles briefly appear and vanish. Energy momentarily concentrates and disperses. These fluctuations are normally microscopic and harmless, but scale them over infinite time and infinite volume, and they stop being negligible. You tend to think of empty space as truly empty. A void, a background where nothing happens. Modern physics rejects that picture completely. What you call emptiness is saturated with fields. These fields do not switch off when matter disappears. They persist everywhere, and they are never perfectly still. Even in the lowest energy state allowed by quantum mechanics, fields fluctuate. This is not a loophole. It is a consequence of the uncertainty principle. Energy and time cannot both be fixed with arbitrary precision. As a result, the vacuum is restless. It flickers. These flickers are not abstractions. They have measurable effects. The Casimir effect, for example, demonstrates that vacuum fluctuations exert real forces. Particle-antiparticle pairs appear briefly before annihilating. These events are fleeting, local, and typically inconsequential. At human scales, they are invisible. At cosmological scales, they accumulate. Quantum field theory does not impose a cutoff on the size of fluctuations. It assigns probabilities. Larger fluctuations are exponentially suppressed, but not forbidden. The vacuum does not ask whether a fluctuation is reasonable. It only asks whether it is allowed. In a finite universe, this distinction rarely matters. The chance of a large, structured fluctuation occurring within the available time and volume is effectively zero. But when both time and volume are unbounded, the arithmetic changes. Infinite opportunities overwhelm exponential suppression. Over infinite space-time, even the most extreme fluctuations occur endlessly, not because they are likely, but because unlikely is not the same as impossible. Probability becomes a waiting game, and infinite patience always wins. This is the bridge between quantum mechanics and the Boltzmann Brain paradox. The vacuum does not need stars, planets, or chemistry to generate complexity. It only needs permission and time. A brain-sized fluctuation is absurdly improbable, but absurd improbability does not protect you in an infinite universe. It only delays the outcome. Eventually, the vacuum explores every configuration consistent with the laws governing it, and the vacuum is everywhere. This matters because vacuum fluctuations are not selective. They do not prefer simple outcomes over complex ones because of meaning or coherence. They prefer outcomes that require fewer constraints. A localized arrangement of particles forming a transient brain requires far less coordination than an entire cosmic history. Once such a fluctuation occurs, physics treats it as real. The configuration exists, the fields are arranged, the processes unfold. There is no distinction between a brain formed by evolution and a brain formed by chance at the level of physical law. The moment the structure exists, the experience exists. You might assume that the surrounding environment matters, that a brain cannot function without oxygen, temperature regulation, or sensory input. But experience does not require comfort or survival. It requires activity. Even a brief cascade of neural-like processes is enough to generate perception. Vacuum fluctuations do not care whether the resulting configuration is viable in the long term. They only instantiate it momentarily, and momentary existence is sufficient for awareness. This is why vacuum fluctuations cannot be dismissed as background noise. In the presence of infinity, background noise becomes signal, not because it grows louder, but because it repeats without limit. Cosmology cannot ignore this because quantum field theory is one of its most successful foundations. These fluctuations are not optional features. They are built into the structure of reality as currently understood. Once you accept both quantum fluctuations and infinite time, Boltzmann brains stop being speculative. They become expected. The unsettling part is not that the vacuum is creative. It is that it is indifferent. It does not distinguish between meaningful structure and meaningless imitation. It produces both, given enough opportunity. Vacuum fluctuations are not a loophole in physics. They are physics. And when combined with cosmological infinity, they force you to confront a universe where awareness can arise without context, without history, and without reason. That realization does not rely on imagination. It follows directly from equations already tested in laboratories. And once you accept it, the paradox is no longer optional. Your trust in reality depends on memory, not just recollection, but continuity. A Boltzmann brain exploits this weakness. It does not need a real past. It only needs the physical imprint of one. Memories encoded as neural states do not distinguish between lived experience and accidental arrangement. From inside the experience, there is no warning signal. Memory feels like evidence. You rely on it to justify your belief that the present emerged from something real. You remember waking up yesterday. You remember learning, changing, making decisions. Those memories feel anchored to events that actually occurred. Without them, the world would feel unmoored. But physics does not grant memory any special authority. At the physical level, a memory is a configuration, a pattern of synaptic strengths, molecular arrangements, electrical potentials. It exists entirely in the present. It does not carry a label that says how it was formed. It does not encode its own legitimacy. The brain treats all memories the same. Whether a memory was built slowly through experience or assembled instantly by chance makes no difference to how it is accessed. The sensation of remembering does not include a verification step. It simply retrieves what is already there. This is why memory is the weakest link in your relationship with reality. You use it as proof of continuity, but it only ever testifies to its own existence. It cannot testify to the process that produced it. A Boltzmann brain takes advantage of this asymmetry. It does not need to fake perception. It does not need to simulate reasoning. It only needs to instantiate a brain state that already contains a convincing narrative. Once that state exists, the deception is complete. From the inside, memory feels authoritative. It feels like a direct connection to what happened. But that feeling is not evidence. It is a feature of how cognition works. Brains evolved to trust their internal records because, in ordinary circumstances, that trust is rewarded. Physics is not bound by ordinary circumstances. You might assume that inconsistencies would give the illusion away, that false memories would clash with perception, that the world would fail to line up with expectation. But a Boltzmann brain does not need a long future in which contradictions accumulate. It only needs a moment. In that moment, the brain's memories can be perfectly self-consistent. They can describe a coherent life, a stable world, even a detailed understanding of physics. The fact that none of it corresponds to an external history is irrelevant to the experience itself. Memory does not check the universe. It checks itself. This is deeply unsettling because it means that your strongest evidence for being embedded in a real, continuous world is also the easiest thing for physics to counterfeit. Not intentionally, but mechanically. The problem is not that memory is unreliable in practice. In your daily life, it works extremely well. The problem is that its reliability depends entirely on assumptions about how the universe usually behaves, assumptions that break down when probability is allowed to explore everything. You cannot step outside your memory to verify it. Any attempt to do so relies on further memories, records, photographs, measurements, testimonies. All of these are present configurations. All of them are subject to the same vulnerability. From a physical standpoint, there is no privileged trace of the past. There is only the present state of the universe, which may or may not encode a genuine history. This does not mean that your memories are false. It means that memory alone cannot guarantee that they are true. The Boltzmann Brain paradox sharpens this into a crisis. It shows that, under certain cosmological assumptions, the majority of memory-bearing minds would have no real past at all. Their memories would be artifacts of chance, not records of experience. If that were the case, then trusting memory would be statistically irrational. That conclusion is unbearable for science because science itself is memory-dependent. Experiments rely on recorded results. Theories rely on accumulated knowledge. Continuity is assumed at every level. This is why memory is not just a cognitive issue here. It is an epistemic fault line. Once memory is undermined, the entire structure of knowing begins to tremble. The Boltzmann brain does not attack reality directly. It attacks the mechanism by which reality is believed, and it does so without leaving a trace that the mind experiencing it could ever detect. No experiment can confirm that your past actually occurred. All evidence of history exists in the present: records, memories, physical traces. If those arise spontaneously, they are indistinguishable from genuine remnants. The paradox does not suggest that you are a Boltzmann brain. It demonstrates that you could not know if you were. You might instinctively search for a test, some decisive measurement that separates authentic history from fabricated continuity. But every test you imagine depends on the same fragile foundation. It consults the present and infers the past. Physics allows no direct access to what no longer exists. A photograph is a present arrangement of ink or pixels. A fossil is a present configuration of minerals. A memory is a present neural state. None of these contain an intrinsic marker of origin. They do not certify how they came to be. They simply are. When you appeal to consistency, the problem deepens. A coherent set of records feels convincing because, in ordinary circumstances, coherence arises from genuine history. But coherence is not exclusive to history. It can also arise from chance, provided the configuration is large enough to encode internal agreement. A Boltzmann brain does not generate random, contradictory fragments. It generates a complete, self-consistent snapshot. Within that snapshot, every record agrees with every memory. Every expectation aligns with every trace. The illusion is total because it is not assembled piece by piece. It appears whole. You might think that physical laws themselves could serve as witnesses, that the universe around you behaves too reliably to be accidental. But physical laws, as you experience them, are also inferred from present observations. They are patterns you detect in how the world seems to behave now. A mind that exists briefly with the right internal states could believe those patterns extend indefinitely, even if no such extension exists. The problem is not that your experience lacks structure. It is that structure alone cannot prove duration. Duration feels fundamental to you because your consciousness unfolds in time. But from a physical standpoint, time does not guarantee continuity of experience. It only orders states. A single state can encode the appearance of a long sequence without having traversed it. You may try to ground certainty in action. You can predict the future, test hypotheses, interact with the world. But prediction also relies on memory. You remember what happened last time. You assume similar conditions will produce similar outcomes. A mind that dissolves moments later will never encounter disconfirmation. The inability to detect the difference is not a failure of cleverness. It is structural. Any method you use to confirm your past presupposes that the past existed. The method cannot step outside that presupposition because it is built from it. This is why the paradox is not solipsism. It does not claim that only you exist or that reality is imaginary. It claims something narrower and more precise, that physics, under certain assumptions, permits observers whose internal evidence is indistinguishable from yours, despite having no genuine history. That possibility cannot be experimentally ruled out from within experience. The limitation is not technological, it is logical. This does not mean that doubt should consume you. The paradox is not asking you to abandon belief in the past. It is showing you that belief in the past is not something physics can ultimately secure. It rests on assumptions about typicality, probability, and the structure of the universe. Those assumptions usually go unnoticed because they are usually satisfied. The Boltzmann Brain paradox drags them into view. You cannot detect the difference because detection itself depends on continuity. It depends on the very thing being questioned. That circularity is not accidental. It is the core of the problem. From inside any conscious moment, the world appears complete. It carries its own justification. There is no internal alarm that signals whether the surrounding reality has depth or is merely an edge. This does not make your experience false. It makes it vulnerable. The unsettling conclusion is not that you are likely a Boltzmann brain. It is that certainty about not being one does not come from evidence. It comes from rejecting universes where evidence loses meaning. And that rejection happens not through experiment, but through choice. Physicists have tried many solutions. Some modify cosmological models to limit the lifetime of the universe. Others propose measures that suppress unlikely observers. Some reject certain forms of infinity altogether. Each solution carries a cost. Each alters fundamental assumptions about time, probability, or reality. Once the Boltzmann Brain paradox was taken seriously, it became clear that it could not be ignored or patched over. It was not a minor inconsistency. It was a structural threat, and so the response was not to dismiss it, but to contain it. One approach is to limit time itself. If the universe does not last forever, then rare fluctuations may never have the opportunity to dominate. Boltzmann brains remain possible in principle, but they never become abundant. This restores typicality by preventing probability from fully exhausting itself. But this solution is not free. It requires the universe to end in a specific way, on a specific schedule. It demands that cosmic expansion eventually halt, reverse, or decay into something fundamentally different. These are not small changes. They reshape the ultimate fate of everything. Another strategy focuses not on time, but on counting. In cosmology, predicting what is typical requires a measure, a way to compare infinities. Different measures weight different regions of space-time differently. By choosing a measure that suppresses late-time observers or favors those embedded in long-lived structures, Boltzmann brains can be made statistically irrelevant. This may sound technical, but the implication is profound. The outcome depends not only on what exists, but on how existence is counted. Probability becomes a matter of definition. Reality is filtered through bookkeeping. Critics of this approach point out that measures can feel arbitrary. Change the rule, change the answer. If the existence of meaningful observers depends on how you choose to count them, then typicality begins to feel imposed rather than discovered. A third approach attacks infinity directly. Some physicists argue that infinities are not features of reality, but signs of incomplete theories. If time, space, or the number of possible states is fundamentally finite, then Boltzmann brain dominance may never arise. This view treats the paradox as a warning, a signal that extrapolating current theories too far leads to nonsense. By rejecting infinite futures or infinite volumes, the paradox dissolves. But rejecting infinity is not trivial. Many of the most successful models in physics rely on it. Removing it can break mathematical consistency or predictive power. It forces theorists to rebuild frameworks from the ground up. Other proposals attempt to change the nature of vacuum fluctuations themselves. Perhaps the physics of empty space changes at very long timescales. Perhaps de Sitter space is unstable. Perhaps dark energy decays. Each of these ideas limits the conditions required for Boltzmann brains to flourish. Again, the cost is uncertainty. These modifications are speculative. They reach beyond currently tested physics. They trade one kind of discomfort for another. What all these attempts share is an admission. The paradox cannot be solved without sacrifice. Something deeply assumed must be given up. Eternal time, neutral probability, unrestricted fluctuation, pure mathematical elegance. There is no solution that preserves everything. This is why the phrase solved is misleading. The paradox is managed, not eliminated. Models that predict Boltzmann brain dominance are excluded from serious consideration, not because they are disproven, but because they are incompatible with the practice of science. This is an unusual move. Science typically adjusts beliefs to fit reality. Here, reality is constrained to preserve belief. The universe must be such that observers like you are not statistical aberrations, or else observation itself loses authority. That requirement acts like a filter. It trims the space of acceptable theories. It quietly enforces a principle that is never stated as a law, that the universe must make sense to those within it, at least statistically. Each attempted solution reflects a different judgment about what is negotiable. Is it better to limit time or to limit infinity? To modify dark energy or to redefine probability? There is no consensus. Only a shared understanding that the paradox cannot be allowed to stand unchallenged. The Boltzmann brain paradox does not yield to a single decisive insight. It yields only to constraint, to the recognition that some possibilities, though allowed by equations, must be excluded to keep knowledge intact. And that recognition leaves a lingering unease, because every exclusion is also an admission. That physics, left unchecked, points toward worlds where meaning collapses. The solutions do not erase that direction. They merely step away from it. One proposed resolution is that eternal inflation must be wrong. If the universe does not produce infinite space-time, then Boltzmann brains may never dominate. This would restore typicality, but at the expense of some of the most successful explanatory frameworks in modern cosmology. The paradox forces a choice between mathematical elegance and epistemic sanity. Eternal inflation was once a triumph of theoretical ambition. It took a puzzling set of observations and offered a sweeping explanation. Inflation explained why the universe appears flat, uniform, and structured on large scales. Eternal inflation extended that success by suggesting that inflation never completely ends. Instead, it continues forever in some regions, constantly spawning new pocket universes. In this picture, reality is vast beyond comprehension. What you observe is a small, local outcome of a much larger process. The framework is mathematically rich, internally consistent, and deeply appealing to theorists seeking unification. It is also exactly the kind of universe where Boltzmann brains thrive. Eternal inflation produces infinite space-time. Infinite volume, infinite time. It creates environments where every allowed fluctuation occurs endlessly. Once that is accepted, the hierarchy of observers becomes unavoidable. Simple observers overwhelm complex ones. Accidental minds outnumber evolved histories. This is not a flaw at the edges of the theory. It is a direct consequence of its core premise. To eliminate Boltzmann brain dominance, some physicists conclude that eternal inflation cannot describe reality, not because it fails observational tests in the present, but because its long-term implications undermine the possibility of observation itself. This is a radical move. It means discarding or heavily modifying a framework that elegantly explains several otherwise mysterious features of the universe. It means accepting that some mathematically natural extensions of successful theories must be curtailed, not by data, but by epistemic necessity. The cost is real. Without eternal inflation, certain explanations lose their simplicity. Fine-tuning problems re-emerge. The universe's initial conditions become harder to justify. The multiverse, as a conceptual tool, becomes suspect. But the alternative is worse. If eternal inflation is correct in its unrestricted form, then the typical observer is not embedded in a coherent universe. Typicality collapses. Scientific inference loses its footing. The success of cosmology becomes a statistical anomaly with no stable justification. This forces a decision that physics rarely has to confront so directly. Which matters more, explanatory breadth or the ability to trust explanations? Eternal inflation scores highly on the first. It provides a grand narrative that absorbs complexity into structure. But it fails catastrophically on the second. It predicts a universe where observation is almost always misleading. Some theorists attempt to save inflation by modifying it. Perhaps inflation ends everywhere eventually. Perhaps the production of new regions slows or halts. Perhaps certain vacua decay faster than expected. Each adjustment trims infinity just enough to keep Boltzmann brains in check. Others argue that eternal inflation was never meant to be taken literally, that it is a mathematical artifact of approximations pushed too far. In this view, the paradox is a sign that the framework has exceeded its domain of validity. What unites these responses is an acknowledgement that infinity is not innocent. Allowing processes to run forever is not a neutral extrapolation. It changes what dominates, what is typical, and what can be known. The death of eternal inflation, if it comes, will not be announced as a failure. It will be reframed as refinement, a necessary correction, a recognition that some beautiful ideas lead to unlivable worlds. This is not unprecedented. Physics has abandoned elegant theories before when they conflicted with deeper constraints. What is unusual here is the nature of the constraint. It is not experimental contradiction. It is epistemic collapse. The paradox does not say eternal inflation is false. It says that if eternal inflation is true in an unrestricted sense, then you have no reason to trust that conclusion. Faced with that, many physicists choose trust. They accept a messier universe, a more limited one, a reality that may lack some of the grandeur once imagined. because a universe that is less elegant but knowable is preferable to one that is mathematically perfect and epistemically empty. That choice reveals something quiet and profound. Physics is not only about what exists, it is about what can be believed. And when those come into conflict, existence is the one that must give way. Scientists often say the Boltzmann brain problem has been solved. What they mean is that models predicting them are now rejected, not disproven, but disqualified. Theories that allow such observers are treated as incomplete or incorrect. The paradox is avoided not by elimination, but by exclusion. This distinction matters more than it first appears. In most areas of science, a problem is solved when a mechanism is identified, tested, and shown to be false or unnecessary. The Boltzmann brain paradox does not end that way. No experiment rules Boltzmann brains out. No equation forbids them. Physics still allows them in principle. What changes is the status of the theories that make them dominant. When cosmologists say the problem is solved, they mean that a line has been drawn. A boundary has been set around acceptable explanations. Any model that predicts a universe where most observers are deluded is no longer considered viable, regardless of how well it fits other data. This is not elimination in the usual scientific sense. It is triage. The paradox exposed a failure mode so severe that it overrides other considerations. A theory can be mathematically consistent. It can reproduce known observations. It can even unify multiple domains of physics and still be rejected simply because it predicts a world in which observation cannot be trusted. That is a rare outcome in science, but it is not arbitrary. Scientific theories are tools for understanding reality. If a tool undermines the possibility of understanding, it ceases to function as a tool. The Boltzmann brain paradox forces this realization into the open. By excluding Boltzmann brain-dominated models, scientists are not claiming that such universes are impossible. They are claiming something narrower and more practical, that such universes cannot be the one we inhabit, because inhabiting them would make knowledge itself implausible. This move shifts the role of the observer from a passive consequence to an active constraint. The universe must be such that observers like you are not statistical flukes. That requirement is not derived from physics alone. It is imposed to preserve physics as an activity. This is why the solution feels unsettling. It relies on a form of reasoning that is rarely acknowledged explicitly. A theory is judged not only by what it predicts, but by whether it allows its predictions to be believed. In effect, cosmology adopts a self-consistency condition. The universe described by the theory must be one in which the act of description is meaningful. Once this condition is accepted, many otherwise plausible models fall away. Eternal de Sitter universes with unregulated fluctuations, infinite inflationary landscapes with no decay. Any scenario where time stretches on without bound in near equilibrium conditions. These models are not falsified, they are sidelined. This is why the paradox is said to be solved, not because the underlying physics changed, but because the standards for acceptable cosmological explanations did. The community agreed, implicitly and explicitly, that some outcomes are unacceptable regardless of their mathematical pedigree. This kind of solution is fragile. It depends on judgment, on shared criteria about what science is for. It does not close the door permanently. A future theory might resurrect these ideas in a safer form or show that the paradox dissolves under deeper understanding. But for now, exclusion is enough. The Boltzmann brain paradox functions as a filter. It removes theories that predict too much randomness in the wrong place. too much abundance of meaningless observers, too little grounding for trust. The price of this solution is humility. It admits that not every mathematically allowed universe deserves equal consideration, that physics must sometimes say not just what can exist, but what must not dominate. This does not mean that reality is shaped by comfort. It means that reality, if it is to be studied at all, must be compatible with study. The paradox is avoided by refusing to live in worlds where avoidance is impossible, and that leaves behind an unresolved tension, because exclusion is not explanation. It is a boundary, not a mechanism. It tells you where you cannot go, not why the universe stays where it is. That tension remains beneath the claim of resolution, quiet, unsettled, waiting. Nothing in physics forbids Boltzmann brains. The solution is not a discovery that they cannot exist. It is a recognition that any universe where they dominate cannot be the one we trust. This is a philosophical constraint imposed on physical law. This is an uncomfortable admission for science. Physics prides itself on deriving conclusions from equations, not from what feels acceptable. Yet here, acceptability becomes unavoidable. The Boltzmann brain paradox forces a distinction between what is permitted by law and what is permitted by knowledge. Boltzmann brains remain physically allowed. Quantum field theory permits fluctuations. Statistical mechanics permits rare configurations. Cosmological models permit long, quiet futures. Nothing in the mathematics draws a hard line that says a mind cannot appear by accident. What changes is how such possibilities are treated. The moment Boltzmann brains dominate the observer population, the connection between observation and reality collapses. At that point, physics loses the ability to ground its own claims. The theory may still exist as a formal structure, but it can no longer function as an account of a world that can be known. This is why the solution is not empirical. No telescope can rule out Boltzmann brains. No experiment can falsify their possibility. The solution is methodological. It concerns what kinds of universes science can meaningfully describe. The constraint is philosophical, but it is not arbitrary. It arises from the internal logic of inquiry. If a theory predicts that almost all observers are mistaken about their surroundings, then it predicts that almost all observations are misleading. That includes the observations used to support the theory. A framework that invalidates its own evidence cannot be retained without contradiction. This introduces an unusual hierarchy. Instead of observation constraining theory, theory is constrained by the conditions required for observation to be credible. The arrow of justification reverses. This reversal feels dangerous because it appears to put human reasoning at the center of cosmology. But that is not what is happening. The constraint is not about human preference. It is about statistical coherence, about whether typical observers of any kind can trust their experiences. A universe dominated by Boltzmann brains is not hostile to humans in particular. It is hostile to reliability itself. Any mind, no matter how advanced, would be adrift in a sea of fabricated continuity. This is why the constraint is imposed universally. It is not about saving your experience. It is about saving the concept of experience as evidence. Once this is accepted, the phrase solved takes on a different meaning. The paradox is solved in the same way that a self-contradictory axiom system is solved, by rejecting it as a foundation. Physics often encounters infinities that signal breakdowns of understanding, singularities in general relativity, divergences in quantum field theory. These are not accepted as literal features of reality. They are treated as warnings that the theory has exceeded its domain. Boltzmann brain dominance plays a similar role. It is not a prediction to be embraced. It is a signal that something has gone wrong in the extrapolation. The philosophical constraint imposed here is quiet but powerful. It says that reality must be such that knowledge is not statistically accidental, that observers who infer laws from experience are not overwhelmingly likely to be wrong about everything. This does not guarantee truth. It guarantees only that truth is not drowned in noise. Critically, this constraint does not specify how the universe achieves this. It does not dictate the fate of dark energy, the structure of time, or the nature of infinity. It only demands that whatever the answers are, they must avoid Boltzmann brain domination. In that sense, the solution is incomplete by design. It marks a boundary, not a destination. It tells physicists where they cannot go, without telling them where they must. This leaves a residue of unease. Physics is being guided not just by what the universe does, but by what it must allow us to know. The universe is being filtered through epistemology. That filtering may be unavoidable, but it carries an implication that lingers, that the deepest laws of reality are constrained not only by consistency and observation, but by the requirement that observation itself remain meaningful. And that requirement does not come from the universe. It comes from the act of trying to understand it. This marks a subtle change in how science operates. A theory is no longer judged solely by predictive accuracy or internal consistency. It is judged by whether it preserves the meaningfulness of observation itself. Reality is filtered by what allows observers to believe in it. You are witnessing a shift that is easy to miss because it happens quietly, in footnotes and assumptions, rather than proclamations. For most of its history, science asked a simple question: does the theory match what we observe? If it did, and if it was internally coherent, it earned its place. The Boltzmann Brain paradox forces an additional question. Does the theory describe a universe in which observation is trustworthy at all? This is not a demand for certainty. Science has never required that. It is a demand for non-pathology, a demand that observation not be statistically meaningless, that evidence not be drowned out by overwhelming unreliability. Once this standard is introduced, the evaluation of theories changes. A model can no longer hide behind elegance alone. It must answer for the kind of observers it predicts, not as an afterthought, but as a central feature. You might expect this shift to feel like philosophy intruding on physics. In practice, it feels more like physics confronting its own limits. The equations did not fail. The interpretation did. When cosmologists began to take observer statistics seriously, they realized that some theories succeeded too well. They explained everything by allowing everything: infinite time, infinite space, infinite fluctuations. But in doing so, they erased the distinction between signal and noise. A theory that explains all possible observations equally well explains none of them meaningfully. The new standard does not ask whether a universe can exist. It asks whether a universe can be known. That may sound like a retreat from objectivity, but it is the opposite. It recognizes that objectivity requires a stable platform. Without typical observers, objectivity has no foothold. This changes how assumptions are treated. Infinite futures are no longer neutral extrapolations. Measures over infinite sets are no longer technical details. They become existential risks to knowledge. The shift is quiet because it is uncomfortable. It acknowledges that physics cannot be completely detached from epistemology, that describing the universe requires assumptions about who is doing the describing and how likely they are to be mistaken. In earlier eras, this problem did not arise because the universe was assumed to be finite enough, structured enough, and young enough that such pathologies never appeared. Modern cosmology broke those assumptions. It opened the door to scales where probability behaves differently. Once that door is open, standards must change. You now see theories being evaluated not just on what they predict, but on what they imply about you. About whether your existence as a coherent observer makes sense under their framework. This is not anthropocentrism. It is statistical necessity. Any observer, human or otherwise, would face the same issue. If a theory predicts that almost all observers are confused, then the act of theorizing becomes self-defeating. So science adapts. It introduces constraints that were never formalized before. Typicality conditions, observer selection principles, epistemic viability. These are not laws of nature. They are laws of inquiry. They do not tell you what the universe must be like in detail. They tell you what it cannot be like if it is to be understood. They function as guardrails, not maps. This represents a maturation rather than a failure. Science is recognizing that explanation has prerequisites. That not all mathematically consistent worlds are scientifically habitable. The unsettling part is what this implies, that the universe physics describes is already filtered, that some possibilities are never considered seriously, not because they are impossible, but because they dissolve meaning. You live inside that filter. Your confidence in reality depends on it. This does not make science circular. It makes it conditional. It admits that knowing requires a world that supports knowing. The Boltzmann Brain paradox did not just challenge cosmology. It forced science to articulate something it had always relied on, but never named. That reality must not only exist, it must be legible. And legibility, it turns out, is not guaranteed by physics alone. You exist at the mercy of probability. Not just in your origin, but in your justification. Your confidence in the universe depends on the rejection of scenarios that are mathematically allowed but existentially corrosive. That rejection is pragmatic, not proven. This is the point where the paradox stops being abstract. It reaches into the assumptions you carry without noticing. You do not merely believe that the universe exists. You believe that it exists in a way that makes belief reasonable. That belief is not secured by evidence alone. It is secured by exclusion. Physics allows many worlds that you quietly refuse to inhabit. You do not reject them because they contradict data. You reject them because living in them would make data meaningless. That distinction matters. It means your trust in reality is not grounded in certainty, but in restraint. In the decision to treat some possibilities as unacceptable, even when equations permit them. Probability governs everything beneath this decision. It governs the formation of stars, the emergence of life, the stability of matter. And at cosmic scales, probability indifferent indifferent to narrative. It does not care whether a configuration supports meaning or erases it. It only cares whether the configuration is allowed. This is why your existence feels less stable the longer you look at it through a cosmological lens. You are not just unlikely, you are conditionally acceptable. Your presence as a coherent observer makes sense only if certain vast regions of theoretical possibility are ruled out in advance. That ruling out is not something the universe announces. It is something science imposes. You might be tempted to see this as weakness, as an admission that physics cannot fully justify itself. But it is more accurate to see it as a boundary, a recognition that explanation has prerequisites, that not all mathematically possible universes are compatible with understanding. The unsettling part is that this boundary is not fixed by experiment. No observation tells you that Boltzmann brain-dominated worlds are impossible. No measurement confirms that infinite time does not exist. The rejection is based on consequences, not causes. If a scenario dissolves the meaning of observation, it is excluded. Not because it is false, but because it makes truth unreachable. This places your confidence in a precarious position. You trust the universe not because every alternative has been eliminated, but because the alternatives that survive elimination are livable, knowable, stable enough to support belief. That is a fragile foundation. It means that your certainty is provisional. It rests on the hope that the universe respects the same constraints that science needs in order to function. That reality does not exploit the full freedom its laws allow. Probability, left alone, would not grant you that courtesy. Given enough time and space, it produces everything, including minds with no past, including experiences with no cause, including observers for whom belief itself is a coincidence. The fact that you are not overwhelmed by such observers is not something you can prove from inside the system. It is something you infer by rejecting worlds where inference collapses. This is the quiet instability beneath existence. You live in a universe that must be restricted for you to trust it. And that restriction is not derived from first principles. It is assumed because without it, nothing stands. This does not mean your experience is false. It means it is conditional, meaning survives only if certain extreme outcomes never dominate. Knowledge persists only if probability is kept in check. The paradox does not tell you that the universe is hostile. It tells you that it is permissive, too permissive to be trusted without constraint. You exist because countless improbable events aligned, but you remain justified only because countless other improbable events are assumed not to. That assumption is not guaranteed by physics. It is a requirement imposed on physics. And once you see that, the ground beneath certainty stops feeling solid. Not because it is gone, but because you understand how carefully it must be maintained. The universe may allow everything, but you can only live in one where not everything is allowed to matter. Even if your universe avoids Boltzmann brains, the mechanism remains real. Random fluctuations exist. Entropy dominates. Probability has no concern for narrative. The paradox is suppressed, not erased. This is why the unease does not disappear when scientists declare the problem solved. Nothing fundamental was removed from physics. The laws that allow Boltzmann brains were not repealed. The mathematics that permits them remains intact. What changed was the decision to treat certain outcomes as unacceptable, not their physical possibility. That distinction matters. You are not protected because the universe cannot generate meaningless observers. You are protected because the universe is assumed not to generate too many of them. The difference between cannot and must not is where the fear lives. Entropy still drives systems toward equilibrium. Quantum fluctuations still ripple through empty space. Probability still explores whatever it is allowed to explore. None of these mechanisms were dismantled. They were only constrained by cosmological boundaries that are themselves uncertain. The paradox lingers because the suppression is conditional. It depends on assumptions about the fate of dark energy, the structure of time, the validity of infinity, and the stability of physical laws over unimaginable durations. None of these assumptions are settled. They are provisional. As long as they remain open, the door is not closed. It is merely held shut. This creates a quiet tension in modern cosmology. On one side, the models that best fit current observations often gesture toward infinite futures and stable vacuum states. On the other, those same features threaten to resurrect the paradox if taken too seriously. You live inside that tension. The fear is not that Boltzmann brains are lurking just beyond the horizon. It is that the universe does not fundamentally care whether observers are meaningful or not. Meaning is not a conserved quantity. It is not protected by any known law. Physics does not promise you a universe that makes sense. It promises only consistency. The mechanisms that generate order also generate imitation. The same randomness that allows life to emerge through long causal chains also allows minds to flicker into existence without them. There is no safeguard that privileges one over the other at the deepest level. The paradox is suppressed by insisting that the universe ends, or changes, or limits itself before the balance tips. But those endings are speculative. They are inferred, not observed. They lie far beyond any empirical reach. That leaves you in an uncomfortable position. Your confidence rests on what has not yet happened, rather than on what has already been measured. You trust that the future will not be long enough, empty enough, or stable enough for probability to overwhelm meaning. That trust is reasonable, but it is not guaranteed. This is why the Boltzmann brain paradox leaves a residue even after it is addressed. It exposes a vulnerability that cannot be sealed completely, a reminder that your existence as a reliable observer is contingent, not absolute. Even in the best-case cosmological models, the universe skirts the edge of this problem. The line between meaningful structure and meaningless fluctuation is not thick. It is a matter of balance, of rates, of asymptotic behavior. The fear lingers because nothing in physics ensures that balance must always favor you. The paradox also leaves behind a philosophical echo. It shows that meaning is fragile at cosmic scales, that narratives dissolve when probability is allowed to run without limit, that history itself can be statistically outnumbered by imitation. You are accustomed to thinking of reality as something that resists absurdity, as something that pushes back against nonsense. The Boltzmann brain paradox suggests the opposite. That absurdity is always waiting, held at bay only by circumstance. Even if your universe avoids it, it does so narrowly. The mechanism remains, humming quietly beneath everything you know. Entropy increases, fluctuations persist, probability does not sleep. The paradox is not gone, it is contained, and containment is never the same as safety. That is why the idea continues to unsettle physicists long after it has been formally addressed. It reminds them that the universe does not owe observers coherence, and that coherence, once lost, cannot be recovered by explanation alone. There is no dramatic conclusion in physics papers, no declaration of safety, only adjusted assumptions and careful language. The unsettling part is not that scientists found monsters in the equations, it is that they quietly moved the equations to avoid them. When the Boltzmann brain paradox is discussed in journals, it is rarely framed as a crisis. There are no alarms, no bold proclamations. Instead, there are footnotes, caveats, conditional statements that subtly redirect the future of a theory. A model is said to be problematic, a parameter range is disfavored, a certain asymptotic behavior is avoided. The language is restrained, almost bureaucratic. But beneath that restraint lies a recognition that something fundamental was at stake. The silence after the answer is deliberate. Physics does not declare victory over paradoxes like this, because there is no victory to declare. The equations did not eliminate the problem. They were constrained to keep it from appearing. That difference matters. Scientists did not discover a mechanism that prevents meaningless observers from arising. They discovered that allowing them to arise breaks the enterprise. So the models were trimmed, adjusted, redirected away from the abyss. This is unsettling because it reveals how much of cosmology depends on choices that are not dictated by data alone. When observations cannot reach the regimes where paradoxes dominate, theory fills the gap. And theory must decide which futures to take seriously. Those decisions are rarely announced. They are embedded in assumptions about stability, decay, or finiteness. They are justified as reasonable, conservative, or natural, but they are choices. The silence reflects an unease about admitting this openly. Physics prefers to present itself as discovering reality, not curating it. The Boltzmann Brain paradox blurs that boundary. When a theory is modified to avoid epistemic collapse, the modification is not falsifiable in the usual sense. It is motivated by the need to preserve meaning, not by a new observation. That makes it difficult to frame as a discovery rather than a safeguard. So the conclusion is muted, the paradox is said to be resolved, and the discussion moves on. But nothing was erased. The underlying mechanisms remain. The equations still point toward dangerous infinities if pushed far enough. The silence does not mean the threat is gone. It means it has been bracketed. This is why the aftermath feels uneasy. You are left with a sense that the universe was edited, not explained. That the most troubling implications were not disproven, only avoided. Physics has done this before. Singularities are hidden behind horizons. Divergences are renormalized away. Infinities are regulated. Each time, the theory survives by limiting its own reach. The Boltzmann Brain paradox fits this pattern. It is not an anomaly to be removed. It is a boundary to be respected. The silence after the answer is the sound of that boundary settling into place. You will not find a final statement assuring you that reality is safe. You will find a gradual consensus that certain paths lead nowhere science can follow. That is all. The unsettling realization is that science continues by choosing what not to say as much as by discovering what to say. It advances by narrowing the space of allowed explanations until only those that support understanding remain. That narrowing is invisible from the outside. To you, the universe still looks vast, coherent, and stable. The equations still work. The predictions still hold. But somewhere beyond what can be tested, certain futures have been quietly ruled out. The silence is not ignorance. It is restraint. It acknowledges that some questions, if pursued without limit, do not yield answers. They yield dissolution. And science, to remain science, must know when to stop. The Boltzmann Brain paradox did not end with a solution. It ended with a decision. And decisions, unlike discoveries, do not echo. Your understanding of reality depends on constraints imposed to protect understanding itself. That is not circular reasoning. It is survival reasoning. Knowledge exists only where observation remains meaningful. This distinction matters because it reframes what knowledge is allowed to be. You often imagine knowledge as something discovered, lying in wait within the universe, independent of the conditions under which it is found. The Boltzmann Brain paradox forces a harsher view. Knowledge does not merely require truth, it requires a world in which truth can be distinguished from coincidence. That requirement is not optional, it is structural. If observation is statistically meaningless, then no amount of reasoning can rescue it. Data becomes noise, patterns dissolve into chance alignments, explanation becomes indistinguishable from hallucination. In such a universe, knowledge does not fail occasionally. It fails by default. The constraints imposed by cosmology are therefore not epistemic luxuries. They are preconditions. They exist to prevent a collapse into a state where knowing anything is no more justified than knowing nothing. This is why the reasoning is not circular. Circular reasoning assumes what it sets out to prove. Survival reasoning assumes only what is necessary to continue. It does not claim certainty. It claims viability. You do not demand absolute guarantees from reality. You demand that reality not sabotage the act of demanding. That distinction is subtle, but essential. Consider how fragile knowledge already is. Even in a stable universe, you rely on inference, memory, and trust in consistency. None of these are infallible. Science works not because it eliminates error, but because error is constrained. Noise exists, but signal dominates. The Boltzmann Brain paradox describes a regime where that balance flips, where noise overwhelms signal, where false observers dominate true ones, where the act of observing is no longer correlated with external reality. In such a regime, the word knowledge loses meaning. It does not become difficult. It becomes undefined. The constraints imposed by physicists are designed to prevent that regime from being taken seriously as a description of our universe. They ensure that typical observers are not statistical outliers, that experiences are not overwhelmingly likely to be fabricated. That inference is not an accident. This is not an appeal to comfort. It is an appeal to coherence. You cannot build knowledge on a foundation where the probability of being mistaken about everything approaches certainty. Even if some observers occasionally get things right, their success would be indistinguishable from luck. Knowledge requires more than coincidence. This realization changes how you should think about truth. Truth is not just correspondence with reality. It is correspondence under conditions where correspondence is meaningful, where reliability is not a fluke. The universe described by physics must therefore satisfy a minimum epistemic threshold, not because humans demand it, but because any observer capable of forming theories would face the same constraint. An alien intelligence, a machine mind, any system that reasons from experience would require the same statistical footing. This is why the Boltzmann Brain paradox is not about human-centered bias. It is about observer-centered viability. It applies universally. Knowledge exists only where observation remains meaningful, because meaning itself is not protected by physics. It is emergent. It survives only in regimes where structure persists, continuity holds, and probability does not erase correlation. The unsettling implication is that knowledge is conditional. It is not guaranteed by the universe. It is permitted by it under certain circumstances. Those circumstances are narrower than you might expect. The constraints imposed to protect understanding are therefore acts of humility. They acknowledge that explanation has limits, that pushing theories beyond those limits does not reveal deeper truth, but dissolves the possibility of truth altogether. You do not know the universe because the universe owes you clarity. You know it because, so far, it has not made knowing statistically absurd. That is a precarious arrangement. The Boltzmann Brain paradox exposes that precariousness. It shows that knowledge is not a default state. It is a narrow corridor carved out of an overwhelming space of possibility. Science continues by guarding that corridor carefully, not because it fears what lies outside, but because outside it, knowledge does not survive. And without knowledge, there is nothing left to explain. This paradox is not abstract. It concerns whether experience implies history, whether memory implies causation, whether existence implies persistence. Those assumptions underpin every moment of your awareness. You rely on them without noticing. When you feel hunger, you assume your body existed moments ago. When you recall a conversation, you assume it occurred in a shared past. When you anticipate tomorrow, you assume the world will still be there to receive it. These are not philosophical positions you adopt. They are background conditions of consciousness. The Boltzmann Brain paradox presses directly against those conditions. It does not question whether the world exists. It questions whether the link you assume between what you experience now and what supposedly happened before is guaranteed by physics, and the answer is not reassuring. Experience, at the physical level, is a present event. It does not carry proof of its own lineage. It feels embedded in a sequence because brains evolved in environments where sequences were real and stable. That feeling is adaptive. It is not evidential. Memory strengthens the illusion. A remembered past feels qualitatively different from imagination. But physics does not recognize that difference. It recognizes only present configurations. A memory that accurately reflects history and a memory that merely resembles one are indistinguishable to the laws that govern them. Causation feels equally solid. You assume that what you experience has causes that precede it in time. But causation is inferred from patterns, not observed directly. You never see causes. You see correlations extended across moments you assume are connected. Persistence ties it all together. You assume that because something exists now, it existed a moment ago and will exist a moment from now. This assumption is so basic that without it, the idea of a self dissolves. Identity requires persistence. Meaning requires continuity. The paradox does not deny these assumptions in practice. It reveals that physics does not enforce them universally. That makes this your problem, not because you are likely to be deceived, but because your certainty rests on conditions you cannot verify from inside experience. You live inside a structure that feels necessary, but is merely common under certain cosmological assumptions. Most of the time, this vulnerability is irrelevant. The universe you inhabit appears stable. Continuity holds, history accumulates. You build knowledge, relationships, expectations. Nothing in daily life challenges the assumption that experience tracks reality. But the paradox shows that this comfort is local, not absolute. It asks you to confront a possibility you cannot test against. That the connection between now and before is something you trust because you must, not because it is guaranteed. That your confidence in persistence is an inference, not a fact. This does not mean you should doubt everything. It means you should recognize what doubt cannot touch. You cannot doubt your experience without using experience. You cannot doubt memory without relying on memory. The foundations are not falsifiable from within. Physics usually does not interfere with these foundations because it does not need to. At ordinary scales, continuity is overwhelmingly supported. The paradox only emerges when you extend physics beyond those scales into regimes where probability overwhelms narrative. But once you see it, you cannot fully unsee it. You realize that the assumptions holding your world together are not laws of nature. They are conditions of intelligibility. They are what make a world livable to a mind like yours. That realization has consequences. It means that your existence as a coherent observer is not just a biological accident. It is also a statistical privilege. one that depends on the universe not exploiting every possibility it allows. You are not wrong to trust your past, but that trust is not anchored in proof. It is anchored in the expectation that the universe is not adversarial to meaning, that it does not generate far more convincing illusions than realities. The Boltzmann Brain paradox does not accuse your experience of being false. It accuses physics of being too permissive to guarantee that experience is true. That accusation lingers because it cannot be answered empirically. It can only be managed by constraining what kinds of universes are taken seriously, and that management happens whether you think about it or not. Every time you plan, remember, or reflect, you are betting that existence implies persistence, that memory implies causation, that experience implies history. Those bets are usually safe. But the paradox exists to remind you that they are bets nonetheless. You experience reality as continuous, structured, and meaningful. Physics allows that experience to be accidental. The Boltzmann Brain paradox is considered resolved only because unresolved, it would erase the very idea of resolution. And that leaves a final question hanging quietly beneath everything you think you know. Not whether Boltzmann brains exist, but what it means that the universe had to be redefined so that you could trust that you do. This is where the paradox leaves you, not with an answer, but with a reframing. You are not asked to accept that your experience is illusory. You are asked to notice the price paid to protect it. Entire classes of possible universes are set aside, not because they violate physical law, but because they violate intelligibility. That decision changes the relationship between you and reality. It suggests that the universe you describe is not simply the most natural outcome of the laws of physics. It is the subset of outcomes that allow description to function at all. Meaning survives not because it is favored, but because scenarios that drown it are excluded from serious consideration. This is unsettling because it inverts the usual story. You like to believe that meaning emerges because the universe is structured in a certain way. The paradox suggests that structure is retained because meaning would not survive otherwise. You are living inside a filtered reality. This does not mean the universe is tailored for you. It means that only certain kinds of universes can be known, and those are the ones that science continues to study. Everything else fades into theoretical exile. The final question is not about existence, it is about justification. Why does the universe permit reliable observers at all, when probability alone would happily overwhelm them? Why does continuity persist when discontinuity is cheaper? Why does history dominate imitation? Physics does not answer these questions. It steps around them. The Boltzmann Brain paradox forced cosmology to recognize that explanation has a horizon. Beyond that horizon, theories may still exist, but they lose their grip on meaning. The universe does not forbid those regions. Science simply cannot follow. This leaves you in a quiet, unresolved space. You trust reality because you must. You justify that trust because alternatives dissolve justification itself. This is not proof, it is necessity. You might wonder whether this makes your existence fragile or privileged. The paradox does not settle that either. It only shows that existence, as you experience it, is conditional on constraints that are not written into the laws of physics themselves. That conditionality is uncomfortable. It suggests that the deepest features of reality are not just about what happens, but about what can be believed to happen. The universe, in this view, is not required to be meaningful. It is required only to be consistent. Meaning persists only if consistency does not explore its full range. And yet, here you are, experiencing continuity, building memory, trusting causation, acting as if the past mattered and the future will arrive. The paradox does not tell you to stop doing that. It tells you that doing so depends on a universe that quietly refuses to exploit every freedom it allows. That refusal is not guaranteed. It is assumed. And that assumption sits beneath every thought you have about the world. The question that remains is not whether your experience is real. It is why reality, out of all it could be, remains compatible with experience at all. Physics, for all its reach, does not answer that. It only draws a line and says that beyond it, knowledge disappears. You live on this side of that line. And the reason that line exists is not written in the stars, but in the necessity of believing that the stars were ever really there.